Previously, we did an example where we were given a curve and we were asked to determine whether the derivative at particular points would give us a positive, a negative, a zero, or an undefined solution. And we did that by approaching the idea of a derivative geometrically, interpreting the derivative at a point x as the slope of the line that's tangent to the curve at that point. Now we're going to do a similar problem, but we're going to be not using any graphs. Now it's all algebra. We just use the formula for this problem. So we examine the given information. We're just given a function, which would be the curve if we graphed it. F of x equals the square root of 3x minus 1. We're asked to find the derivative f prime of x. So they're not asking for a value, a real number value. They're just asking for a function that represents the slope of the line that's tangent to the curve at that point. We shouldn't be thinking just as the geometric interpretation. This is just a general rate of change problem. We're getting a formula that has x values that we feed into it to give us the rate of change of the function at a particular point, an arbitrary point x. So let's recall the formula for the derivative. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Now apply this function that we're given, the square root of 3x minus 1, and that gives us a limit of the square root of 3 parenthesis x plus h close parenthesis minus 1. In other words, we evaluate the function f for x plus h and then minus f of x, which is the square root of 3x minus 1 over h. Now this problem calls for multiplying the quotient by the conjugate of the top over the conjugate of the top, and that's because if we don't do that, we're going to do direct substitution and end up with an indeterminate form of 0 over 0, which we don't want to deal with. So we multiply by the square root of 3 parenthesis x plus h minus 1 plus the square root of 3x minus 1 over itself. So you see, this is the conjugate of the numerator over itself. And we can use the formula across the top. This is a minus b times a plus b, so it's equal to a squared minus b squared. So we have the limit of the first 3 parenthesis x plus h minus 1 without a radical anymore because we squared it for a squared minus b squared minus parenthesis 3x minus 1. And on the bottom, we leave our h out in front. We're going to multiply these two terms under the radicals. And at this point, we're going to do some cleanup on the numerator. And when we do get rid of the parentheses, things start dropping out and we're left with just 3 times h in the numerator of this quotient. So the limit is the limit of 3 times h over the h in the denominator times this mess in brackets, which shows us that we have a common factor of h on the top and bottom, which will easily cancel. So after writing the rest of the denominator, we'll go ahead and cancel out the factor of h on the top and the bottom. So now we have a limit of 3 over square root of 3x plus 3h minus 1 under the first radical in the denominator plus the square root of 3x minus 1. Let's go ahead and take this limit now. Let's let h go to 0 in this rational expression, and we get two terms that match in the denominator. The square root of 3x minus 1 added together gives us 2 of those guys. So we have 3 over 2 times the square root of 3x minus 1. Aha! This is not a real number, of course. It is a function of x. It has an x in it. That's great. That's what we were expecting. So let's compare. Let's see. Let's tell them what the function f's domain is and the function f prime of x's domain is. First, the domain for f, just take the radicand, set it greater than or equal to 0. You get x is greater than or equal to 1/3. Write it in interval notation here. That's the domain of the original function f, from which the derivative was derived. But the domain of the derivative itself Well, the only thing we want there is we want to make sure that we don't get a zero denominator. That makes it more complicated than the previous domain. So we cannot include the 1/3. We have to exclude the 1/3 in this interval from 1/3 to infinity. So they have similar, in this case, they have similar domains, but not exactly the same. And I mentioned the domain because I really want to emphasize that the answer that we got when we took the derivative of this function was again a function of x.